Okay, so we are on now. So it's recording. Everyone, enjoy the session. I'll try to show up again later. Rakvi, the floor is yours.
Okay, thank you. Yeah, so as discussed and suggested last time, I am actually using two devices, one to share my screen and one to share my audio. So I hope this works fine. But of course, if you have any questions or if you cannot hear my voice at any moment, please just let me know or just raise or just unmute yourself and ask the question. Okay, so yeah, so before I start today's lecture, any questions from last time or uh, any questions from first lecture? Anything that I should go over again? Just please let me know. Okay, so looks like there are no questions. So I'll just get started then. So focus of today's lecture will be finite fields. But before I discuss that, I just want to recall what we saw about fields last time. So this is a recap from previous lecture that recall a field F is first of all is a set with two binary operations that I'll call addition and multiplication, such that, well, if you consider this set along with this operation, this is an abelian group. And by binary operation, I simply mean, as discussed last time, that it's a rule or it's a way of composing or adding two elements in the given set F. So it's just a rule. So I take two elements in F, I sort of apply this rule, and I get back an element which lies again in my set. So this is what I mean by binary operation. So this is an abelian group. If you consider, uh, if you remove 0, which is the identity of addition from this set, and if you consider this set under multiplication, this is also an abelian group. And obviously there are two things going on, and there has to be some relation between them. And this relation is called distributive property. So what it means is that if you take two elements, you add them, and if you ask what is A dot B plus C, this is simply A dot B plus A dot C, and it works both ways. Okay, so right. And we also saw some examples. For example, if you simply take this set of rational numbers and the addition and multiplication are usual, so this is usual addition or the natural addition, or like I'm sure everybody knows how to add rational numbers, and that is the addition that I'm thinking of, and this is the usual multiplication. So if you take this, then this is an example of a field. All right. And we also saw a non-example. By non-example, I mean that a set that you're really, really familiar with. So let's take the set of all integers. And again, On integers, I have the usual addition and multiplication, right? I can add two integers, I can multiply two integers. This is not a field. What I have always found useful is that whenever you learn something new in maths, obviously it's helpful to see a lot of examples. But what is more helpful is to see what fails, or to see why something is not an example. So this is not a field. So let's go back and try to see what actually fails here. So under addition, it is an abelian group. That is all right. But under multiplication, this fails to be a group because it fails to have multiplicative inverses. So for example, if you take 2 and if you ask what is that integer such that 2 times x is 1, so there is simply none, right? So this is not a field. This is, however, this is a ring, right? So Z is a ring that fails to be a field. If you want to think of multiplicative inverses, you have to go to rational numbers, right? And there it becomes a field. So you have to extend your set. Anyway, so we are, yeah, and today I want to talk about finite fields. So before that, I want to talk of a concept that is associated to fields. It's called characteristic of a field. Actually, it can be associated more generally. It can be associated to a ring also. Okay. So characteristic of a field slash ring. So if you take any field or any ring also, remember what is the difference between ring and a field? The only difference is that a ring might fail to have multiplicative inverses, right? But there is still the operation of multiplication and identity exists, right? So you take any field or ring, you always have this one object called 1. And when I say 1, don't just think of the usual 1 or the natural number 1 that we are used to, but rather think of this more generally, like the multiplicative identity. When I say 1, I really mean the general multiplicative identity of a ring or a field. And this might change how it looks, right? For example, Q, it is the usual number 1, or Z or N, it's the usual number 1. But when we think of matrices, this will become the identity matrix, right? Because if you take any matrix, you multiply it with identity, you get back that matrix, right? So it change this keeps changing from set to set, but I'm talking about a general multiplicative identity here. So in whatever field or ring you take, right, there is this always 1 present, and there is another element present which is 0, which is additive identity, right? Again, this 0 might change its look depending on the set we are in. If we talk about matrices, then this 0 is really the 0 matrix, right? So there are always these two elements present, and we always have addition, right? We know how to add two elements. So if I start with 1, I can ask what is 1 plus 1, right? Or for shorthand notation, let me just call it 2 times 1. Or in general, n times 1, right? 1 plus 1 plus 1. Just keep to it n number of times. And you can ask, what is this, right? I mean, what is, this is another element of a ring, right? But let me ask a question. Is it possible that n times 1 is 0 for some n? So the answer to this question, it depends on your field. Okay. For example, if I ask this question for Q, so the answer Short answer is both yes and no. Okay. And it depends on the field we are in. So, for example, over Q, if you ask this question, so 1 is our usual natural number 1. And if I ask this question, is n times 1 equal to 0, where n is a natural number? The answer is obviously no, right? You keep adding 1 to itself, you keep getting new numbers, but you never get 0, right? But there are fields besides Q, right? So this kind of a situation is called characteristic zero situation. So what is characteristic? So here is a definition. Characteristic, so let F be a field. Let F be a field or a ring. Okay, same definition works for a ring also, or a ring. So the characteristic of F, let's say we denote it by, or write it as C char of F. Okay, this is just a notation. Is the smallest natural number n such that n times 1 is 0. Okay, this is my characteristic. But we just saw an example where n times 1 is never 0, right? In that case, what do we say? So if no such n exists, we say that characteristic F is 0. I mean, if you go by the definition, technically it should be that characteristic of F is infinity, right? Because no such smallest number exists. You keep going for larger and larger. But instead of saying infinity, we say it's 0. Um, so just an aside. So just an aside. So if we take any, so we just saw an example of a characteristic 0 field, right? Q are good old rational numbers. These are characteristic 0 fields. But are there others? So suppose F is a characteristic 0 field. Then what can I say about F? I mean, it's a vague question. It's a vast question. What can I really say about F? But here is one quick observation. Okay. Obviously, as we know that 1 belongs to every field, right? And I can add. So 1 plus 1 belongs to F. So which is 2 times 1. Let me just say it's 2. Okay. And then similarly, just going on. So n belongs to F, right? So what can I observe is that a copy of natural numbers is obviously contained in my F, right? You just keep on adding 1 to itself. Now it's a field, right? So it's a group under addition. So I need to have 0 and I need to have additive inverses also. So what does that tell me? So 0 and additive inverses are there. So that tells me that a copy of Z also sits inside my F, right? And now that I have Z, I need to also have multiplicative inverses, right? And when I do that, so because F is a field, right? multiplicative inverses are also there. So that tells me that Q sits inside my F. And this is a very important observation, right? Um, Not that we will use characteristic zero fields much, but just as I said, this is just an aside. So if I have any characteristic zero field, a copy of Q always sits inside it, right? Or this kind of inclusion is another way of saying this is that Q is a subfield of F. By subfield, I just mean that it's a subset, which is a field in its own right, and they share the common identities. Okay. So Q is a subfield of F. So any characteristic zero field is basically an extension of Q or a field extension, right? So another phrase to say this is that F is a field extension of Q. Anyway, so let's go back to our. So this is all about characteristic zero. Now I want to discuss about non-zero characteristics. Okay, so non-zero characteristic. Is Q the greatest common subfield in a characteristic zero field? Uh, just to phrase this question better, are you trying to ask that if we take all the characteristic zero fields in the universe, then is Q the greatest common thing that we can get? Yes, yes. Yes, that's true. Q is the greatest common thing you can get. Um, so yeah, sure. So non-zero characteristic. Okay, so this is the setup. We have our field, and characteristic of F is a natural number not equal to 0. Now here is a first observation about what can n be. So we are in a field, right? F is a field. So if I tell you that, okay, here are two numbers in F, and by numbers, I just mean like not necessarily numbers, but two members of the set. Okay. So I take two members of the set, I multiply them, and I tell you their product is 0. So what can we say about A or B here? Okay. Um, and let me also say that neither of them are equal to 0. Okay, there is a follow up to the previous question. Does this mean that Q is a subfield of every characteristic zero field? Yes, yes. This is what I just discussed in the aside, right? So if we start with any characteristic zero field, one is there. So you keep adding, so you get natural numbers. So you throw in additive inverses and 0, so you get integers in there. Now you include the multiplicative inverses. So that's how you get Q, right? So every characteristic zero field has Q as a subfield. That is correct. Yes. Yes, Crystal, your answer is perfectly correct. Uh, your answer is perfectly correct. Either A and B has to be 0. I further impose that, well, yeah, if A or B are 0, then obviously A times B is not obvious, not exactly obvious. So, okay, here is a tiny exercise. Uh, so here is a small homework exercise for everyone. So homework exercise 1. Show that if A or B is 0, then A times B is 0. So in integers, it's obvious, right? But here we are talking about general fields. So why this property sort of holds in general also, this is something that it's a nice exercise to show. And you only have field axioms at your disposal, right? So try using field axioms to show this property. Anyway, so what if A and B are non-zero? So from what I know, so let's assume that neither A or B is 0. But remember, we are in fields, right? And what do we know about fields is that if you take a non-zero element, it has a multiplicative inverse. So we have this equation, right? Let's just multiply it with A inverse. Okay. So what we will get? So multiply this equation with A inverse. So A inverse times A times B is A inverse times 0, which by our homework exercise, so A inverse times 0 is simply 0. And now look at A inverse times A times B. Well, we also know that multiplication is associative, right? So the brackets don't really matter. So this is simply A inverse times A times B, which is 0. But what is A inverse times A? This is 1, the multiplicative identity. And what is 1 times B? Well, 1 is the identity, right? So B is 0. Right? So this already gives me a contradiction because I assume that both A and B have to be non-zero, right? So what this tells me is that you cannot multiply two non-zero elements to get 0, right? One of them has to be 0. So if I have a non-zero characteristic, what this tells me is that this characteristic cannot be composite, right? Because what goes wrong if n is composite? Let's just take a small example. um oh, I can we can discuss this in general also. So suppose n is composite, right? So you can write n as product of m1 times m2, smaller numbers, right? And n times 1 is 0. Moreover, n is the characteristic. N is the smallest number for which it happens. But n is basically m1 times m2, right? So m1 times 1 times m2 times 1, that has to be 0, right? But n is my characteristic. So I know that m1 times 1 and m2 times 1, they both have to be non-zero because they are not the characteristic, right? But I cannot have two non-zero numbers giving me 0. So this is the this is a small proof that n cannot be composite, because this would fail, because in fields basically I cannot have two non-zero numbers giving me 0. So what this tells me is that n has to be prime. Okay. So this is our first observation, that if I have a field f, and if I know that its characteristic is non-zero, then characteristic has to be a prime number. So again, there are two kinds of things for these finite characteristic fields. So either the field itself is finite, which are finite fields, or there can be another thing. Uh, Let me discuss about this box slightly later, because I'll need some notations from finite field setup, but let's try to fill this box slightly later. Okay. But what I want to say is that just because characteristic of a field is finite or a prime number does not necessarily imply that the field itself is finite. You can have an infinite field with finite characteristic. Anyway, so that brings to that brings us to finite fields. So what are these? Okay, so let me just start with talking about within finite fields. Let me start talking about fp. So what does this notation mean? F sub p. So p is a prime here, right? And not necessarily odd prime. It can be 2 also. So this is a field that contains exactly P elements. Okay. And how is this constructed? What is this field exactly? So let's take an explicit example. So let's just take P equal to 7. So what is F7? So first of all, what I do is, so let's go back to integers, okay, and think of division here. So P equal to 7, this is my set, okay, F7. As a set, it has to consist of 7 elements, and here are my elements: 0, 1, 2, 3, 4, 5, 6. There are 7 elements, right? But don't think of them as single elements. Rather, think of these elements. So each element here is actually a class. Okay, it's just a representative of infinitely many things. Okay, so this 0, so think of these numbers as remainders when we divide mod operation. Exactly, remainders when we divide by, I was trying to avoid that word, but you're right, this is mod operation. Remainders when we divide by 7. So if you, in general, if you divide by any number n, there are possible n remainders, right, from 0 to n minus 1, and n is basically 0, right? So this is how we identify. So 0, 1, 2, 3, 4, 5, 6, these are distinct classes of remainders. And how do we add and subtract? Well, we add and subtract naturally, but then we go back to its remainder class appropriately, right? So just to take an example, 4 plus 5. 4 plus 5, so add it like natural addition. So 4 plus 5 is 9, right? But 9 is not in our set. 9 as, just if you think of 9 as 9, it's not in our set. But if you think of 9 as a remainder, you can find it in our set. So 9, when you divide by 7, you get back the remainder 2. So 4 plus 5 is actually 2 here. Okay. And 4 times 5, which is 20. But now think of remainder of 20, right? So if you divide 20 by 7, you get remainder as 6. So this is how we add and multiply. In general, if we have fp for any p, so here are the p elements: 0, 1, 2, 3, 4, all the way up to p minus 1. And how do we add and subtract? Just like before. Okay. So a plus b is a remainder mod p, and so is a dot b. Now, why this is a field? It basically comes from, so let me just write it down. So the reason fp is a field is because of Euclid's lemma, the fact that you can write GCD as a linear combination of two integers. Okay, these things. So it's let me know if you want to see a proof of why fp is a field. Otherwise, I can leave it as an exercise and you can show that fp is a field. Okay, so yeah, I think there is a question. Oh no, there are no questions. Okay. Yeah, if yeah, let me know if this exercise is is a bit too much, or I don't know. I can We can discuss in class also why this forms a field. But let's continue for now. So these are examples of finite fields, but these are not all. Okay. So FPs, as you take P to be a prime, are examples of finite fields, but these are not all. In fact, you take any power of prime. So you take any prime P, take any power of it. Okay. P square, P cube, P to the power 4. Corresponding to that, you can get a field of that order. And in fact, these are all the finite fields. Okay. So if you take this double set, sort of, so f p to the r, where p is a prime and r is a natural number, are all the finite fields. Okay. And it's a, in fact, if you fix your order, there is exactly one field up to isomorphism. So this concept of isomorphism is also quite interesting. So what it means is, just to give a basic example, is let's say I have a field of three elements, 0, 1, 2. But here is another way to think of a field of three elements. So I can just think of different representatives, for example, like -1, 0, 1, so to say, right? But what is crucial here is these are isomorphic. What isomorphism means is that the sets need not be exactly equal to each other. Okay, so they are not equal in the sense that the sets are not, the sets do not match up on the nose, right? But what do we really care about when we think of fields? We care about the operations, right, and the identities and everything. So under that identification, these two sets are like, I don't want to think of these two things as really different. For me, these are same, right? So these are a set consisting of three elements. I have additive identity, I have multiplicative identity, and I can identify how I add and multiply in a natural way, right? So that's what I mean by isomorphism. So my sets may be different, but when it comes to the properties that I really care about, these are really same. Okay. So I don't want to think of them as different fields, really. So if you fix a order, if you fix a prime, if you fix a power, right, there is exactly one field up to isomorphism corresponding to that order, right? So finite fields are really corresponding to each number, like each number of this type, they're really unique. But what are these things? So let's take an explicit example. So let's just say we have f2. So we know what f2 is. Two elements. We know how to add and multiply. 0 plus 1 is 1. 0.1 is 0. 0.0 is 0. 1.1 is 1. And now I want to think of field of four elements. Okay. A first natural instinct is to just go back to the mod operation or the mod construction, really, right? But that doesn't really work, right? So if we go back to our mod business, what will I say? Okay, so I'll take the remainders 0, 1, 2, 3, right? But that doesn't really cut the, it doesn't really solve, it's not a field. Okay, so this construction is not correct. Why is this not a field? Let's take an example. So what do I want? So in a field, we know that if we take two non-zero numbers, and yeah, exactly, if we take two non-zero numbers and if we multiply them, I can't get zero. But let's just take two here. If I multiply two with two, I get four, which is basically zero, right? So this is not a field. So this construction is not correct. So mod n construction is not correct. Instead of this is what I really do. So f4, right? So this is 2 to the power of 2. So here is the construction. So my first business is I look at the degree, okay? And the degree is basically the power. So 4 is 2 squared. So I'm looking for degree 2 polynomials over f2. So my first business, my first task, if I want to construct this field, is to describe all the degree 2 polynomials over f2, okay? And what does a degree 2 polynomial look like in general? Well, so there is an x square term, there is a degree x term, and then there is the constant term, right? And a, b, and c are my numbers. So when I say degree 2 polynomials over f2, degree 2 polynomials we all understand. Over f2 means the coefficients come from f2. So a, b, and c are members of f2. And they are not hard to describe because f2 only has two elements, right? So my this uh, tuple of three elements a, b, and c can take 8 possibilities, okay? So let's just write down all of them and also write down the polynomial corresponding to them. Well, the first possibility obviously is they all can be 0. So 0, 0, 0. So my polynomial is also just 0. 0, 0, 1. So that gives me 1. 0, 1, 0. That gives me x. 0, 1, 1. So that gives me x plus 1. 1, 0, 0. That gives me x square. 1, 0, 1. That gives me x square plus 1. Uh, 1, 1, 0. That gives me x square plus x. And then 1, 1, 1. X squared plus x plus 1. These are the 8 possibilities, and I've listed down. Okay. So in the process, I've not only listed degree 2 polynomials, I've also listed the constant and degree ones, but I don't care about them. Okay. So I look at degree 2 polynomials, and there are exactly 4. These 4. Okay. So x squared. Now my next task. So first thing was to list all degree 2 polynomials over f2. My second task is to look for polynomials that don't factorize degree 2, of course. That do not factorize. So what do I mean is, like, for example, if you look at x square, well, this is just x times x. So I don't want these. Okay, these are really bad. I want to avoid these. Now, x square plus 1, you might think that x square plus 1 doesn't factorize, but we are talking about factorization over f2 here, not over rationals. Okay. And in fact, x square plus 1 does factorize. X squared plus 1 is actually just x plus 1 whole squared. Because if you just think about it, x plus 1 squared is x squared plus 2 times x plus 1. But we are thinking of these polynomials who are f2, right? 2 times x is 2 is just 0 for me. So this is in fact x squared plus 1, right? So this factorizes. X squared plus x also factorizes. X times x plus 1. X squared plus x plus 1. This doesn't factorize. Okay. We can check. It's you don't have to take my word for it. You can actually check this. Okay. So try. So if you want to factorize one of the factors, like both the factors have to be degree 1, right? So try constructing two degree 1 factors. We know all the degree 1 polynomials, right? X times x and x plus 1 are really the two ones. So try taking products of them and we can see that this is neither. Actually, we have constructed all the products. X times x is x squared, x plus 1 square we already found, and x times x plus 1. This doesn't factorize, okay? So this is our candidate, okay? So we found one. So x squared plus x plus 1 is our guy or girl or person. Anyway, this is our candidate. Let me just say it's a candidate. Uh, I wasn't trying to be sexist. Sorry, it's a candidate. Okay, so now what do we do with this? And okay, this is just to pause here, just as an aside. In this particular example, like over f2, when we are looking for degree 2 irreducible polynomials, we found exactly one. This is not necessarily true. Okay. So in general, if we are over fp and we are looking for some degree r irreducible polynomial, there is no reason that there is a unique one. There can be more than one. Okay. So this is a special example in which we exactly found one candidate, but this doesn't have to be the norm. There can be more than one. Okay. But what I'm going to do next doesn't affect that thing. Okay. So in fact, in general, choose any irreducible polynomial of your choice, or maybe the first one you encounter. Okay. So now this is so here is what I do. So I take f2 and I take all the polynomials with coefficients in f2. Okay. So this is set of all polynomials in one variable, and that variable I have called x. Okay. Any degree. I have no constraint on the degree. Take all the polynomials of all the degrees, but the only constraint is that it should be in one variable and with coefficients in f2. Okay, throw in all the polynomials here, but coefficient should be in f2 and single variable. All right. Now this, again, this is a small homework exercise. I forget the number. Maybe it's 1 or 2. I don't know. So check that this set f2 of x is a ring. Now, if it's a ring, there must be some addition and multiplication. So how do we add and multiply two polynomials? We add coefficient wise, and then we multiply using distributive property, right? So I will just say under usual addition and multiplication. Okay. This is a ring, but now I have an irreducible polynomial, so I have to use that also, right? So I'm going to construct a quotient ring. Now, what do I mean by that? So I take this ring, all the polynomials, and I quotient it out by, so this was my polynomial, x squared plus x plus 1. Okay. This is my notation for quotient ring. What does this mean is, so keep this example in mind. So think of really Z mod mz. So mod m, the example of remainders that we just discussed, like for example fp, the things that we just called fp, right? These are basically Z mod pz. So instead of m, let me just use p because this is more familiar, at least in the context of today's lecture. Okay, so think of Z mod pz. So what do? I identify two numbers whose remainder modulo p is same. And this is exactly what I do in this polynomial also. Okay. I identify two polynomials such that when you divide by x squared plus x plus 1, now in polynomials also we have a division algorithm, right? This is one thing common between polynomials and integers. You can divide two integers. You can also divide two polynomials, right? Uh, I'm sure everybody is. In any case, let me know if you want to see polynomial division or how it works explicitly, right? Please let me know. I'm assuming that we are familiar with dividing polynomials. Anyway, so we can divide two polynomials, right? Like we can divide two numbers. So this set is just like the mod p numbers. I take two polynomials and I identify them if they leave same remainder when divided by x squared plus x plus 1. Okay. So what are all the objects here? What are all the objects here? So let's try to think of them. Now, this is a slightly challenging exercise. So, challenge homework. Again, let me just repeat myself. If any of these homework exercises you would like me to do, or you would like to discuss it together in a lecture, please let me know. Okay, I'm more than happy to do that. So, this is a slightly challenge homework. This object f2x mod x squared plus x plus 1. So, show that this object is a field. So before we do that, let's just list down. Let's just see before we think about this exercise. Let's just try to list down all the elements as a set. What does this look like? Okay, and in fact, so this was my claim. Okay, this is a field, and this is what I'll call as F4. Okay, so I started. So F4 is 2 square. Okay, so my base is always F2. So I take all the degree 2 polynomial. And why degree 2? Because 4 is 2 squared. So squared. Okay. Don't we have to show that this is an ideal for the quotient to make sense? Well, this is an ideal. I mean, I'm taking the ideal generated by x squared plus x plus 1. Okay. So what is this? Okay, so what is this? So let's just discuss this ideal also. So what is x squared plus x plus 1? Angular brackets. Okay, what is this? So this is basically all the multiples of x squared plus x plus 1, right? Where f belongs in f2 of x. You can show that it is an ideal. Under what circumstances a quotient ring becomes a field? Not always. Not always. Okay. So in general, if you take a ring and if you just take an ideal, it's not guaranteed that it will be a field. It's just a quotient ring. Okay. But if you have a polynomial ring, like I had here, if you have a polynomial ring and you take the ideal generated by an irreducible polynomial, then that quotient is a field. Okay. So I'm using something very specific of polynomials here. So yeah, so this is my ideal, and you can show, sorry, this is just my set, and you can show that this is an ideal. I mean, 0 is here, and then it is closed under addition, and then you can show it satisfies the properties of ideals. Okay. I had forgotten. It's a I mean, yeah, if you take this set, all the multiples of x squared plus x plus 1, then you can check that it satisfies all the properties of being an ideal. So it is an ideal. Okay. For those who are not familiar with ideal and quotient rings, you don't have to worry. Uh, we don't have to know this sophisticated terminology for what we are going to discuss next. Basically, what why I'm discussing finite fields and why do I want to show this construction in detail, because we'll be discussing elliptic curves from next lecture. And for elliptic curve cryptography, we'll be focusing on points over finite fields. Okay. So I just wanted to make sure that we know what finite fields are, what these objects are, right? And how do we basically work with them. We all have, like, we all have to be comfortable with addition and multiplication. So that's all we care about. So if you are familiar with this terminology of ideals and quotient rings, great. Like, this is a special case of a very general construction in that case. If you're not familiar, then that's also great. I think I have discussed whatever we need to know. Anyway, so this is my field and this is what I'll call f4. Okay, degree 2 extension of f2. So let's just see some like explicitly what this set is and how do we add and multiply. Okay, so f2 of x, let me just say this aside, uh, ideals. So f2 of x mod this thing. Okay, so first observation is that I'm dividing by degree 2 polynomial. Okay, so I'll have my constants are okay, degree 1 polynomials are okay, even certain degree 2 polynomials are fine. But whenever you go to degree 3 polynomial, you divide by x square plus x plus 1, you will land up with a remainder that is either 0, 1, or 2, right? So all we have to care about is describing polynomials up to degree 2 essentially. So what are these things? Let's just do that. And we want 4 elements, right? So I obviously have my constants 0, 1, and then I have x and x plus 1. And everything bigger than that can basically is equivalent to one of these things. Right? I hope I'm not missing out on it. There are 2 constants and then yeah, I want degree 1 polynomials, right? So ax plus b. So 0, 0 gives me 0, 0, 1 gives me 1, 1, 0 gives me, and then 1, yes. And anything, yeah, basically if we take degree 2 and onwards, like for example, x square, well, x square is just equivalent to x plus 1, right? Because x square is x square plus x plus 1 times 1 minus x plus 1. So this is our remainder, minus x plus 1. But then minus 1 is plus 1, so it's x plus 1. Like that, right? So anything can be attributed to. You take any polynomial, it will be equivalent to these 4 polynomials. These are the 4 elements. And this is my field now. Okay. So how do I add? So think of, if you can think of these as polynomials. You can also think of them as tuples if you wish. Okay. So 0 is really 0, 0. Why 0, 0? Just how I showed, right? So we have 2 tuples, A and B, and then we have AX plus B. So this is all I'm doing, right? So if it is 0, 0, we get 0. If it is 0, 1, we get 1. 1, 0 gives me x, and then 1, 1 gives me x plus 1. Right? These are my polynomials. So if we want to add, we can add the tuples, corresponding tuples, coordinate wise, or simply just add the polynomials. For example, if we want to add x plus 1, this is 2x plus 1, but 2 is 0. So this is 1. On the tuple side, what is this? So I'm adding 1 comma 0 plus 1 comma 1. And I'll add coordinate wise, right? So this will just give me 2 comma 1, but 2 is 0, so this is 0 comma 1, and 0 comma 1 corresponds to 1. So this is my point. So there are just 2 ways to think about it. Okay, and how do I multiply? just again, just coordinate wise. Okay. So 1.0, sorry, 1 comma 0. And 1 comma 0 is simply x. Okay. Or if you want to think of polynomial multiplication, then x times x plus 1 is x squared plus x. But x squared plus x is really x squared plus x under this identification. It's really just 1. Wait. Wait, let me not. Oh, I think I made a mistake in tuple. Anyway, let me stick to polynomial addition and multiplication here. But yeah, I think addition is good. You can also think of addition via the tuple part. So x squared plus x is just 1, right? Because we are dividing by x squared plus x plus 1. So x squared plus x is simply x squared plus x plus 1 times 1 minus 1. So remainder is minus 1, but minus 1 is plus 1 for us, right? So this is how we add and multiply. And then you can also check that each of these non-zero elements have an inverse. So for example, 1 is inverse of itself. X's inverse is x plus 1, because x times x plus 1 is 1. X plus 1 inverse is x, and so on. And so yeah, so this is in fact a field. Just an example. In general, so same thing would hold. So this was an example of F4, right? Same thing would hold for F8 also. Or in general, if you start with a finite field on its base and you want to construct Fp to the R, for example. So what is this construction? Is basically you quotient it out by an irreducible polynomial of degree R. Okay. Same thing. I mean, the obviously the set would change. Uh, If you explicitly want to see what the set is, obviously that will change. But this will give you a field. And in fact, here is a remarkable theorem. So I said previously, right, that in this example, we were lucky, or not lucky. I mean, this is just a coincidence that when we are looking for degree 2 irreducible polynomials, we found exactly one. But this is not necessarily the case always. Okay. In general, if we are looking for degree r irreducible polynomials over Fp, there can be more than one. So in fact, if we take two different ones, so you can do this construction. And what is amazing is, even though f and g are different polynomials, the quotient ring, which is a field that you get, that are isomorphic. Okay. So the choice of polynomial doesn't affect my field eventually. Okay. You can choose different polynomials to construct, but the object is ultimately isomorphic. So there is exactly one field. So there is exactly one field, finite field of a given order up to isomorphism. Okay. So this is our, yeah, these are our finite fields. And this was just an example. So just just as a small exercise, I would really encourage you to play out with F8. Okay. So find an irreducible polynomial of degree 3 and then construct this explicitly. So construct F8 explicitly and try to work out how addition and multiplication works. Okay. So just to wrap up this topic on finite fields, what I said was that if you take a field whose characteristic is prime, so we get finite fields, right? And by the way, just for clarification, this F4, okay, this F4 has 4 elements, but still its characteristic is 2. Its characteristic is not 4, right? Because you can see that 0 is obviously 0, so let's just forget 0. 1 plus 1 is 0, right? 2 times x will also give me 0 because 2 is 0, right? And x plus 1, if you add it to itself twice, so you get 2x plus 2, which is basically 0, right? So even though this field has 4 elements, the characteristic is still p, right? So in general also, if you take field extensions of fp, this has p to the power r elements, but the characteristic is still p. So if we take characteristic p fields, we get finite fields. Where was that? Finite fields. But there are other class of things also. For example, what I can do is I can take this polynomial and sort of take its quotient, or let me just use this symbol. What it means is that I don't just have polynomials, I also have quotient of polynomials to make it a field, right? But here the coefficient comes from fp, right? So this is still a characteristic p field, but now this is infinite, okay? This has infinitely many elements. All right, so yeah. So let me just finish here, wrap up here, and then we'll start with elliptic curves from next week. Okay. Oh, there is a question. For the power 2 F4, it seems that the constants were not enough. Had to move to polynomials. Is there a power down the road that something different happens? No, no. See, so you should think of these things as some sort of comparison thing. Okay, so just to explain this thing better, think of it like this. So always keep this example of integers in mind. Okay, so we have integers and then we have polynomials. So how do we compare two integers? Like how do we say that one is bigger or smaller than the other? We use their absolute value. Okay, so we use absolute value to compare. Likewise, in FP, we don't have such a thing as absolute value, but we do have degree. So we use degree to compare, right? So if I tell you that, okay, try to give me all the elements of Z mod PZ, what do? Basically, we take all the positive numbers, right, whose absolute value is smaller than P. So that's why 0, 1, 2, 3, 4, all the way up to P minus 1, right? If I ask you to do a similar thing here, FPX modulo F, where F is irreducible, then now what can you do? So likewise, you will use the degree, right? So this is basically all the polynomials such that degree of G is strictly smaller than degree of F. Okay. This is just how we compare things. So degree is like a measure, or degree is a sort of way to compare for us in polynomials. So when we were doing this example, f2 of x, we are looking at all polynomials whose degree is strictly smaller than 2. So 0 and 1 also counts, right? So that's why we had 4 elements. Down the road, what will happen is that instead of 2, if you take a degree 3 polynomials, you will have constants, linear, and degree 2. In general, if you take degree r polynomials, then you have to go all the way up to degree r minus 1. Okay? So, yeah. Did I answer your question? Yeah. Okay, great. Yeah. Yeah, of course. Yeah.
Okay. So is that it? The end of the session, I guess?
Yeah, I think I short by 4 minutes. So, but I think we
Okay.
started 3 minutes late, so I guess I'm okay. Yeah.
Yeah, no. This is cool. I
Yeah.
think later you will share the slide, so I can put it on the GitHub repo for the thing.
Yeah, I will
Mm.
just send it to you right now. Yeah.
Okay. So does anyone wants to make any comment or any suggestion or something or anything? Let me stop recording actually, because this actually it turns out some people I would also be the same, be reluctant to feel free to